let's start with number 4 and walk through that one, because number 2 was the other one. I think there's number 4 questions that we might actually clear up a lot of this. So we're building our foundation of reaction stoichiometry, which are taking our reactions, knowing how to write out our products from this prediction, you should know how to predict my store products, and then the mole relationships, the 3 mole relationships, and connecting them with that bridge, the mole ratio. So sometimes it's weird, but we can get to moles from anything. We can get from moles from particles, from grams, from liters, or from molarity and solution liters, right? This is gaseous liters, which is the 22.4 relationship. Solution liters is more like a milliliter and like a liquid volume. So we've got our reaction. We went through the first part yesterday. So it's moving a little slow here. We walked through taking our liters times our molarity, and molarity is moles per liter of solution, and so you write as a fraction, and that allows you to cancel out your liters here. And then we got our moles of sodium sulfate. And that right there was our one of our reactants that we were starting with. And the question for part A said to take our information given and find the grams of precipitate. Well, grams of precipitate, what we all knew was asking of us was the barium sulfate, because we figured out previously that was our precipitate. So we should have been able to go from moles to moles, which was our bridge, our mole ratio. That was a 1-to-1 ratio. And then our last step was just getting to barium sulfate grams, which was 233.39. And that got us to 0.28 grams barium sulfate. So I know you guys got that. Just a quick reminder, we're good with that. The second part said another combination of givens. So anytime you're given a molarity and a volume, you just do M times V, and that will get you to moles. But the only caveat is that the V, the volume, must be in liters, because if it's not in liters, the moles per liter from molarity won't cancel. So you have to get it to liters first. So it's a little slow. Sorry, I got you here. Okay. So we took our 50 milliliters, and I just wrote that, just dive back in the decimal up 3 places as 0.05000 with all of our sig figs, right? Liters. And then you're going to multiply that by the molarity, where the molarity is moles per liter. It's just like saying density. Well, density itself isn't a unit. Density is grams per milliliter. So molarity itself is not a unit, really. It's actually a derived unit. It's moles per liter of solution. So those liters cancel. And then our question was, how many milliliters of the barium nitrate solution will be needed to react completely, right? So question is just milliliters of that solution. So we know in the end we're going to have to use that, but we're not really quite sure to use it now or later. So I'm just going to remind you that this is a conversion factor, that 0.01, and that's, in our case, this is 0.010 moles per 1 liter of solution. That's moles of barium nitrate. And I can flip a conversion factor. Remember, conversion factors are just fractions. You can flip it whichever way you need to based on the units that you're trying to cancel. So we might use it like that, or we might flip it. It depends on in the end right here. So once we get our M times V, we got moles of sodium sulfate. We had to get from apples to oranges. So we had to get from sodium sulfate to barium nitrate, which was using this, which came from what? Where does the 1-to-1 come from? The BC, right? The ratio given from the BC. And then we went from moles of barium nitrate, and the question was how many milliliters of barium nitrate. So the only relationship that can get you from moles to milliliters of a solution or liters of solution is the molarity. And you actually can see that this is the molarity, 0.010 moles per liter, and I flipped it because I needed liters on top at the end because that's what was asked of me. So you can take the molarity and flip it. It's just a tool for you to use if you're trying to get from moles to a volume of solution. So this is moles per liter, and that liter, since it's asked to go to milliliters, I just had to do that last step of getting from liters to milliliters, which is a metric conversion of 1,000 milliliters per liter, and that in the end gave me 500 milliliters. Actually, no, I think this one I needed to fix the decimal. So, did you guys get 50? You got 50. You got 500. You got 50. Okay, yeah. So this one I think the decimal was supposed to be there, but I didn't write it. I pre-solved this, so I can write it all out for this now. So, and Scott, tell me your logic here on B. This was the one we talked about yesterday. Okay, so we talked yesterday, and he said it's the same molarity for both of those solutions. And those barium nitrate and sodium sulfate reacted in a 1-to-1 mole ratio. So if they're the same molarities, the same concentrations, and they react in a 1-to-1 mole ratio, they should require the same number of moles or the same volume of each other. So he looked ahead and he was like, oh, it's just going to be 50 milliliters. And then I said, oh, you got to show it to me mathematically. But it does make sense because it's a 1-to-1 ratio. They require the same concentration, so that they are going to also require the same volumes, which is why this is 50 and that's 50. So it does work out that way. Part 3, or C, said if you make 2.5 moles of the precipitate, which is our barium sulfate again, how many grams of the other product will be formed, right? So when it says that, this initial informations are given, the question's grams of the other product, so it's being really elusive because it doesn't want to tell you what the other product is. Well, we already knew it was sodium nitrate. And then it asks us to take, my word's not online, sorry. So we're going to eventually get from moles of A to moles of D, to grams of D. In this case, we have to take our moles using our, what's this again? Mole ratio to get to the other thing, which is sodium nitrate in this case. These numbers came again from the BCE. And then we took our moles of sodium nitrate to grams, and our final answer should be 425 grams of sodium nitrate. Who got all these so far? I know this was the harder of the 4. Okay, some of us did. Questions I can answer on this one before I go over another one. Some of you guys probably just want to check your answers on number, I think number 3, I didn't tell you the answers for it. Right? Okay, so let me see if I have number 3 right here. Yeah, okay, so let's check these real fast. Actually, if you could not write the reaction, you probably couldn't get much done. But if you can't write the reaction, you should go back and look at your notes or ask somebody, or even if you have to find it online, don't let that stop you. That should not be, you have every resource known to man, okay? You shouldn't stop. Oxide and water will always make a hydroxide. That's a synthesis reaction. So that's one of the ones we talked about previously. In this number 1, raise your hand if you got 1.9-ish. Yeah, okay. Some of our molar masses might be slightly off because I have like this special here I can memorize in my head. So yours might be slightly different. They will publish them differently, just if I got a decimal or 2. Okay, next one. B, your answer should have been 1.10. Yeah, thumbs up. Cool. And then C should have been 103 grams-ish. All right, which of these do I need to go over, or do you just need to see if you made a mistake? Sometimes you just need to see that you're good. I think somebody said part, yeah.
For part A, why is it the mole ratio 3/1?
So I'm comparing moles of the product, and so the product in this case is aluminum oxide. Did you get the correct BCE here?
Yeah.
Okay, so the product, it doesn't say who it is, but you know the product is aluminum oxide, which has a 2 for its coefficient. And the comparison is to the aluminum oxide, which I have a 1 for my coefficient here. So that's why my mole ratio is a 2-to-1, because I'm comparing these two, not these two. So yeah, you have to read because it says product. It doesn't say, it sometimes will be kind of secretive because it doesn't want to do the reaction. You have to know the reactions. Another question on number 2 or 3, guys? Here's part B again and part C. If not, I'm going to move on to our next, kind of our last topic for this unit, and I'm not going to volunteer. Who's really good at making sandwiches? Come on. Okay. Really good at making sandwiches. So, we're going to talk about this now. We're going to talk about like a percent yield. You come on this side because we got to see this. We got to see this magic. So you guys know I worked at like ice cream places. I don't really make sandwich places. What is, before I move on, let me scooch back here. Hold on. Okay, what is the correct recipe for the best PB&J? Matt, what's the recipe? Okay, so we need peanut butter. Do we have peanut butter? That's the peanut butter. Look at that, tasty. It's smooth. It's super smooth. Okay, what kind of? So we got peanut butter, and what else? So we got a slice of jelly. Slice of jelly there. Okay, and how much bread? We need 2 slices of bread. Okay, so I'm going to time you. I want to see how many of these sandwiches you can make. Ready? Okay. 3, 2, 1, go. 2 slices of bread, peanut butter jelly, boom, 1 done, guys. Okay, count with me. She's working it. 2 done. Not too much jelly, it's gonna get soggy. 3. I don't have any more piece of paper. What? What? Hold on, how many did you make? Hold on.
I'm out of bread.
You're out of bread?
4.5.
She made 4.5. She's out of bread, guys. Okay. Oh, so what happened? So we have an what did you say?
Half.
We have an excess of jelly and peanut butter. What do we run out of?
Bread.
Run out of bread. What terminology would you think we should use in terms of the chemistry behind this? Who is the limiting reagent? Bread, like limiting reagent, limiting reactant. So we ran out of bread. So who halts the process of making product? Bread. Who's in excess? Jelly. Do you think that's wise? Think about, like, I don't know if you guys buy groceries or even look at the cost of anything. Bread, about a loaf of bread's, no, $2, okay? A jar of peanut butter is like a big, nice jar, could be $6, $7, $8. Jelly, $3, $4. So do you think it's wise for us to have all this excess peanut butter and jelly? So maybe it'll last for a long time, but what if it's something that is now contaminated because they've been mixed in a big, like, I don't know, blast together? Ew. No, have you guys seen that peanut butter jelly that's actually mixed? Is it good? I'm not so sure. So that could be wasteful, right? So sometimes we need to know exactly the amount we want so we don't have an excess. And it would probably make sense to have the limiting one to be the most expensive one because we don't want to waste it. We don't want to be excess and all contaminated and junk with all the other things in the flask and people, not using clean glassware and clean knives and stuff like that. So you can now see what the limiting reagent does to a reaction. What does it do? So it stops the process and it limits the amount of product made. Okay, thank you, sandwich maker. Two-year-old Daniel. Now I got it. So that's what we're going to talk about today. But we're going to talk about in like a chemical reaction sense. This is a chemical reaction. It just can be physically combined together and then digested and stuff like that. So we'll talk about this in a minute. So think about limiting reagents. Keep it in the back of your mind. Let's go over what you guys just wrote down. I have jokes for you today. So when we talk about making products, when we talk about making yield, that means the amount of stuff we can make in a reaction. Well, the amount of stuff on paper, theoretical yield, this is what I call la-la land, because we are not perfect human beings. And theoretically, we should be able to make, we should probably theoretically be able to solve world hunger and climate change and all that stuff, but is that the reality of it? Maybe not. We're going to be working on that. So in the lab, we have this theoretical yield of what we should be able to make. We should be able to make 10 grams of sodium chloride if we're trying to make some table salt, right? But this is la-la land. Do I have la-la land? Okay. La-la. Okay. It's going to be on paper. Probably not going to be what's happening in the lab itself because there's always these extraneous circumstances that might limit the amount of product we can make. So what do we actually make? We actually call that actual yield. We're not creative with our terms at all, okay? We actually make in the lab. And that's going to be something that you guys will see on the paper saying, Matt recovered 10 grams of sodium chloride. He actually made 10 grams of sodium chloride because that's the terminology used in the problems. So this will be what we calculate on paper, and we're going to call that the theoretical yield. And then the actual yield is what's actually made in the lab. What do you think is going to be the higher number usually? Probably theoretical. Usually the larger number, because we have this like perfect situation on paper, nothing can go wrong. But in the lab, sometimes things go wrong. So it's generally going to be a smaller number. And so, smaller number. And so generally we're going to compare these and get a % yield. Yeah. Sometimes if there's contamination, so like for example, if we have water in our product and we're trying to dehydrate the water all out, what if you heat that baby to never, until the end of the world? You heat it, all the water's going to go away. So it's going to be probably a smaller yield than what we think. But what if somebody dehydrates for like 5 minutes and like, I'm done? What do you think's still left in there? Probably some water. And then they mass it and they're like, I got so much more yield. I'm the best. We're like, no, you just didn't dehydrate it. So sometimes the water can be left over and it would skew the results. Good question. So let's talk about %. If I'm talking about % yield, you know how to do %. All you're going to do to calculate % yield is you're going to take the actual yield that you got in the lab or on the paper where it says actual yield. You're going to divide it by the theoretical yield, which is usually the larger number, and then you're going to multiply by 100, and that will be our percent yield. So if you were an awesome chemist, what do you think a good percent yield would be? What number? 100 would be great, but that's La La Land, people. Like, I'm not feeling, we're not perfect. We're humans. So close to 100, though, so give me something else. 95% yield would be great. I settle for a little less. I'm thinking like 85% and higher is a good yield. Sometimes, like I worked in a lab at UNC this summer, sometimes the yield was like 40%, and they're like, hallelujah, I got some 40% yield. I'm like, you guys are like happy about 40%? They said sometimes you get like 10% yield, and you just like, okay, I'll try again tomorrow. So sometimes in the lab, like the real world, it's a little rough. So I've got a comic for you here. Oh, sorry, before I move on, these yields just need to be represented in the same unit, and you can use them together. So that might be grams, moles, or liters. There's no special unit you have to use. They just have to be the same unit on top and bottom, and you can get percent yield that way. Only because the units cancel themselves out, so it doesn't matter. They just have to be the same. Okay, so my comic. 4.5 hours in the lab, $175 worth of glassware, 17 trials, 3 attempted suicides, 0% yield. Because this is sometimes a little rough, sometimes a lot. So anyway, that's my chemist guy. And then from like a Boss purifying percent yield, 9.63. So sometimes it's not great. And then lab grade based on percent yield, spend an hour pathetically scraping every last grain of product off the glassware. Sorry, we do that in AP Chem because I give them extra credit. They get the best percent yield on some of their labs, and they're really trying. And one time they worked on this lab for 3 days trying to purify a substance, and then one person accidentally spilled their solution. It was liquid. They spilled it, knocked it over, and it crystallized on the countertop. So it was like sludge on the countertop, and they were scraping it. I was like, guys, it's all contaminated. We don't care. We need the percent yield. So then I gave them extra credit for either percent yield or purity. So their purity was crap, but their percent yield was great because they have like all kinds of dust and dirt and stuff in it. So yeah, that was pretty fine. Okay, so let's try our own. The question is, what's a percent yield? So stop there. How do you find percent yield? Good. Actual yield over theoretical times 100. Okay. Oops. 100. So that's really what our question is. So let's kind of piece together what we have and what we don't have yet. So what's the percent yield when 14 grams of magnesium chlorate decomposes and 3 liters of the gas are collected at STP from decomposition? Ooh, a lot of information, right? So let's look at this in a little more detail. What is this going to maybe be in this problem? It's going to help me find theoretical yield because this is not the product, right? This is the reactant. Remember, yield is always concerning about products. So 14 grams is going to be a part maybe to get me started on theoretical yield. Keep going. What do you think we should do with this? James, write the equation. So let's go ahead and do that. Magnesium chlorate. Think, right? Go for it, Peyton. MgClO3, 2, good, because magnesium crisscrosses charge over. Decomposes, think. Alina, what kind of product does it make? What kind of gaseous product does it make? You're right, so keep going. Okay, so we know it makes oxygen gas because chlorates break down to oxygen gas, and you said metal chloride, which is what in this case? Magnesium chloride, so MgCl2, because the crisscrossing down. Okay, and then I need to balance this. What I need, guys? 3 in front of the oxygen, and that's it, right? Yeah, okay, good. So we got our balanced chemical equation. Okay, so 14 grams of magnesium chloride decomposes, and 3 liters of the gas are collected. What information is this telling me? That is what? This is my actual yield. This is saying that much gas is collected. Well, what's the gas? Oxygen gas. Okay, so our actual yield is 3 liters of oxygen gas. So that's something that we know is going to go in our numerator when we get there. So what's really our question still? If we know the actual yield, we're good there. What else do we need? Theoretical yield. Okay, at STP from the decomposition. We know STP is important because it's going to give us that chance to do the conversion with what? Volume, right, 22.4 liters. Okay, so that's going to be good for us. So like we had, Evan said, 14 grams of magnesium chlorate is going to give us a start to get to theoretical yield. So what unit am I going to have to go to so I can implement that whole percent yield combination up there? Okay, so you know I got to go to moles first, but tell me long term, what unit am I looking for at the very end? Liters of what? Oxygen, because my actual yield's in liters of oxygen, so my theoretical yield also has to be in liters of oxygen. So that's our question. So let's get there. I'm going to move this. Okay, so what's my first step? Chase. Right, so somebody give me that molar mass. Teamwork, make the dream work, people. Magnesium weighs 24.31, plus 2 chlorines, 35.45, plus 6 oxygens, 16. What is it? 191. Anybody else? I can pull my notes. I just want to make sure. So 190.9 is what I had written originally, so I'm going to stick with that for now. Okay, so that's giving us to moles of magnesium chlorate. Avery, what's next? What's my next step going to be? Right, so I'm going to go to oxygen. How? Using my mole ratio. So what's my mole ratio? How many magnesium chlorates are there? One. From the BCE, it says 1 magnesium chlorate. And how many oxygens are there? 3 moles of oxygen. Okay, Nicole, what's my last step? Because I've gotten to grams of magnesium chlorate, moles of magnesium chlorate have been taken care of. I'm in moles of oxygen. I need to get to liters of oxygen.
Now, like, do we have to, like, put, like, oxygen bombs that cancel out?
So mole oxygen on bottom, and then what's my liter conversion? Jasmine, what's my liter conversion? There's a 2 in it. 22.4. 22.4 liters of oxygen are STP with 1 mole of oxygen. So then from there, moles of oxygen go away, liters of oxygen are done. So I'm trying to make sure everybody's on board. You should be an active member here, right? So we have 4.928 liters. Now I'm just not rounding yet because it's not my final answer. My final answer will be the percent yield. So what yield is this again? Theoretical. This is la land. If I were perfect in all ways, I would make about 5 liters of oxygen. Well, this person made 3 liters of oxygen. Let's see what their yield was. Anybody got me yet? What I got to do?
3 divided by 4.9.
Okay, so you're going to do actual yield, which is 3 divided by our theoretical yield of 4.928 liters times 100. What's their percent yield? So around that, so like 61 or 60, or I'll go 60.9, so there's 3 sig figs throughout this, yeah. 60.9%. Are they a great chemist or what, guys? No, not great. Not bad, not the 10%, but we're looking pretty good here. Okay, so I'm just going to say this now. Most people will confuse percent yield and percent error. Remember percent error from way back, unit 1? Percent error was whenever you did the error of like the desired, the actual, compared to your experimental. So percent error is when you do actual minus experimental over actual times 100. So is error, do you want error in your experiment? No. So what's a good percent error? 0, right? So something like 15% or less. Something small is a good amount of error. You don't want a lot of error. So small error is good. That percent yield, what do you want? You want high yield. So that's why they're actually opposites, but people mix them up all the time. Okay, so just make that clear so you're not like, I remember this. Okay, so we did that. So this information, I think you can paraphrase now because we saw Maddie's epic failure of making enough sandwiches for all of us. But she was limited by the number of, everybody's she's limited by the LR. Okay, the LR is called the limiting reagent. So you can abbreviate here, but it's going to be the reactant that controls the amount of product you can make. Abbreviate where you need to. And I'm going to try to do one or two big problems with this so you have a sample, and now let's go to yourself. So the limiting reagent in our example here was our bread. But all the excess, so instead of saying excess all the time, I just write XS. The excess reactants are the ones that are left over. So that makes complete logical sense. So what we will do in a problem or in a real life scenario sometimes is figure out if I use this amount of bread, how many samples can I make? If I use this amount of reactant, how many products can I make? And sometimes it's nice to know how much you have left over of everything. So we're going to quantify all of these. And so that's why I walk you through on the next step, how to determine the limiting reagent, and then what do you do from there. So most of our stuff, very first thing is write the BCE. And you will have already done that because you can see that we're talking about reactants and products. You will have written the BCE down. And then our next step is going to be looking at the reactants amounts. Sometimes they're given in grams, and you'll be converting to moles. Sometimes they're already given to you in moles. You're awesome. We compare moles to moles because we have that mole ratio to compare with. So that's why you have to get to moles first. Sometimes it'll be given to you in atoms or molarity and liters. You got all these different ways now to get to moles. So first step, get to moles. After you get to moles, you'll compare the reactants in a special way, and I'm going to model that for you. And that comparison will then reveal to you who the limiting reagent is, or the LR is, and we'll move on from there. So once we get the comparison done, compare with coefficients, then we're going to use the LR to solve the rest of the problem. The problem sometimes will have like A, B, C, D parts. It'll say who's the LR, how much excess reactants left over, how much of this product can we make, and then maybe one more question related to that. So most of these will have a lot of questions asked about it, but once you do the process, you can answer everything because it's all in one big table. So I'm going to show you guys how to do that as we go. So here was our sandwich example with all the excess reactants. Can I go through an example now? In just a second. Oh, wait a second. So I usually teach this in two different totally different styles and ways. But all my AP students said, you've got to teach this method because they said it's so much easier and they understand it better. So I want your feedback as we're going because I've got another way I can teach it too. I learned it a third way. There's like 3 different ways to teach this. So let's try from here. Ooh. Okay. So I want you guys to write down the givens first and let's talk about it and then we'll move on to solve it. Okay. So the reaction between iron and copper 2 nitrate, they react. So we'll think about that. And then it gives us information about grams of iron that are reacting. It gives us information about the volume and the molarity of the copper 2 nitrate that's reacting. And then the questions, the 3 big questions are, what's the limiting one? How much the copper will precipitate. So we already know copper is precipitating in our reaction. And how much the excess reactants left over. So there's a lot of questions asked right around this one reaction. So what do you guys want to start with? Balance equation. Good. So let's start with that. I'm going to write that down. And I think I'm going to try to show you exactly how to write something on paper because we're going to make a big table about it. So write your reaction so it's kind of spread out some, okay? So iron, Fe, plus Cu. Everybody's got to be writing this down. I want to see some active calculations, everything. Copper 2 nitrate is Cu, NO3, 2. Good. Yields. What kind of reaction is this? Single replacement or single displacement, right? So is iron active enough To replace copper? Yeah, copper is really low. It's not so cute. Iron's like, yeah, let me get with nitrate. Okay, so commonly irons. I think I told you guys 3 yesterday, right? Let me make sure I used, yeah. Iron 3 will be our most common charge of iron. So then, what's our product here? Cu, yeah. Copper's been displaced, and NO3. 3, because iron's crisscrossing at 3 now. So then we need to balance it by putting a 3 in front of the copper 2 nitrate and a 3 in front of the copper, and so you see the 6 nitrates here, 2 in front of this to distribute, because this 2 distributes all the way back here to the 3. So that's 6 nitrates, and I have 2 in front of the iron, so there's a 2 here for the iron. Okay, so we're starting off with a pretty challenging one, so let's work this together. I've written it big, so we're going to set up something called a BDA table. So before the reaction starts, D for during the reaction, and A for after the reaction. So along the side here, make it kind of like take up the whole paper, I don't care. Put B, D, A. Before, during, and after. And then we're going to make a little grid system so you don't mix up your columns. So right underneath like the plus sign, or maybe a little over, I need some space. So I'm trying to segment my reaction so that I can see the columns. Like this whole column is for iron, talking about what's happening to iron, talking to copper 2 nitrate, copper, and iron 3 nitrate. And then let's talk about what's happening during the reaction. So before the reaction begins, how much do I have of everything? How much do I have of iron? How much? Before the reaction begins, how much do I have of iron? 3.6 grams of it, right? I have 3.6 grams. What did I tell you? The very first thing we always have to do is convert to moles, right? So let's, right here in this little box, right here for the before, I'll even put a line this way so we can keep the before all kind of happy in one place. We're going to have 3.6 grams of iron, and I'm going to squeeze it in here, okay? You probably have a little more space than I do. 3.6 grams of iron times its molar mass, right? So what's iron's molar mass? Look at the periodic table. How much is it? 55.85. So I don't have space to do it, so I'm wrapping it down. So 1 mole of iron weighs 55.85 grams. How many moles is that? Calculate. I'm trying to calculate with you, so I'm not going too fast. Small number, right? Point what? 0.0645 maybe. I'm going to expand out one more. Okay. So we have 0.0645 moles before the reaction begins. We're all comfortable doing that. How am I going to find the moles for the other reactant? Using this information, how do I find the moles? Maybe remember this from homework last night? Look at your number. Yeah, Scott. Say again? That's molar, right? That's right. So we're doing in our box, or we're going to do M times V to give you moles. We are going to use this a lot. So don't forget, big M is molarity times V in liters will give us moles. So this molarity, and I'm actually going to put the molarity first this time, 0.51 moles per liter. That's what big M stands for, moles per liter. It's like density, which is a derived unit. We have to just write it as a fraction. We're going to multiply that by the liters that we have. Well, how many liters is 5 milliliters? 0.005, right? So we're back in the decimal up. 1, 2, 3. So that's 0.005. So we're going to multiply that by 0.005 liters. And this is just over 1. There's nothing here, okay? So what unit cancels? Liters, right? So liters cancels here and here. This was grams and grams that canceled, so we got moles of iron there. How many moles of copper 2 nitrate do we have here? 0.00255 moles. Good. Okay, so we're all good with getting to moles. We can get to moles from anything. So that's before the reaction starts. How many products do you think we have before the reaction starts? Say again? 0. There's nothing here. Put a big 0 here and here. There are no products before the reaction starts. If not, then that would be really rough, because then we can never stop things from reacting, right? So we've got them separate right now. There's this many moles of the iron and this many moles of the copper. So here's what I want you to do. I want you to sum this in your head. You think about it, you calculate it. But let's see. If I have, and I'm actually going to write the word have here, because this is just a terminology thing that you might want to keep in the back of your mind. This is how much you have of each of these reactants. If I have 0.0645 moles of iron, how much of the copper 2 nitrate would I need to fully react with all of it? Well, it depends. It depends on the ratio in which they react. They react in a 3:2 ratio, right? So 0.0645, I would need to say I need a 3:2 ratio of it. So I want you in your calculator to put 0.0645 multiplied by a 3:2 ratio. So 3/2. How much does that say you need? 0.096, blah, 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 right? Of what? What's it saying? What's it talking about? So what you just wrote, what you just put in your calculator was this. And this is the part I'm always worried about if you understand what the meaning behind it is. So here we go. What you just did was 0.0645 moles, and this is of iron, right? And you multiplied it by 3/2. Well, what's the 3 referring to? Moles of what? Copper 2 nitrate, right. And that 2 is referring to moles of iron. So when you multiply and you cancel out your moles of iron, this says you needed 0.09, what was it, 67? Okay, 675 moles of what? Copper 2 nitrate. So what you just did was you said you needed that much copper 2 nitrate to fully react with all the iron. How much copper 2 nitrate do we have? 0.002. Do we have that much? Yes or no? Not even close. So that right there says, if I need that much, who's going to run out first? The copper 2 nitrate. Because I need 0.09675 to react with all this nice iron. But I only have 0.0025, so I'm totally going to run out of that first. So if I run out of this first, what do I know about it? Is this the LR or is this the excess? This is the LR. So once you know the LR, write it on top of it so you don't forget. That one's the LR. That one's the excess. So that's why I said sometimes I don't want you to dismiss it, because this right here is how you figure out who the LR is. But what we just did was we utilized the comparison of the ratios. So if this is 3/2, we got this. What if this had been like, I don't know, 0.00001? What would your conclusion be? You would say you need, go for it, Scott. Right, because if this was like 0.0001, you would say, oh man, I got plenty. I've got plenty because I have 0.02 here, and I said I only need like 0.0001. So that would mean I had plenty, and that would be an excess, and this one would have to be the LR. Do you see that logic a little bit? We'll keep working on it though, because I want to make sure you're good with it. Okay, so the next part on our little method we wrote down, we said find the LR, convert to moles, find the LR, use the LR to solve the rest of the problems. So what's going to happen to the LR? How much of that's going to be left over after the reaction? 0. So the LR, I know I'm going to have 0 left at the end of the reaction. That's the rule. You have 0 left. You know you're going to have a surplus of this, and you're going to make product. So in a reaction, what happens to the number of reactants as they react? Do they go up or go down? Does everybody understand? Reactants get reacted, they go down. So I'm going to subtract a number of reactants from the first one, the second one. But what happens as those get reacted? What are they making? They're making products, right? So I'm going to add on the product side. So the numbers that I'm adding are all going to be based around who? The LR moles, because it's all based on the number of moles that you have of the LR. They control the products made. So I already know I'm going to have to subtract all of this LR. So I'm just subtracting 0.00255 moles of this. You got me there? We know that makes 0. So for the other reactant, it reacts in a special way. It reacts with this guy, and so I'm going to write minus 0.00255 moles, but reacts in a special ratio. And the ratio is always correlating with the guy that you're talking about, the reactant you're talking about, over the LR you're reacting with. So your ratio is going to be whatever you have here, which is 2, over the 3 that you're reacting from. So the coefficient for the LR is always in the bottom of the fraction for every single one of these, because this is the ratio in which they react. For every mole of copper 2 nitrate, you have to react 2 irons for every 3 of those. So let's do this one. I'm still going to use the same number, the LR number, 0.00255, but what is the ratio in which it reacts? Go for it, Scott. Right, and this 3 on top is referencing who? The copper solid, and this 3 on the bottom is referencing the LR copper. So remember, you're always putting the LR's coefficient on the bottom. And then again, I'm adding the same, 0.00255 moles, but in what ratio over here? Right, 2 for the one you're talking about, over 3 for the LR amount, because the LR is controlling the amount of product. So calculate, boom, boom, boom. So this one you're going to do, you have to subtract. So you're going to do 0.0645 minus this. Tell me what this is when you get there. And then keep going on the others. I'm going to get everybody kind of caught up here. It's like a humongous math problem. Joy. So did you guys get for the first column, you have excess of iron 0.0628 moles. Yes, and then copper 2 nitrate we knew ran out was our LR. The copper solid made was 0.00255, and the iron 3 nitrate was 0.00170 moles made. So walk me through this again. Very first step was what? Balance equation. Second step. Moles of both what? Reactants. That's all I have to start with. I got some units. I got to convert them to moles. So we got both of these. And then how do we compare to see who the LR was? Say again, Maddie. We looked at the ratios. I usually just pick the first one. We'll go, okay, I got this many moles in the first one. How much would I need of the second one? And that's when I compared my ratio and I said, oh, I need a lot of copper 2 nitrate. So then logically, you're like, I need a lot. I have a little. That's going to run out. That's my LR. You have to talk to yourself as you go through. And then once you figure out your LR, what did you do with that number? Subtracted it from itself and also from the other reactant, but in a special ratio of its 2 over the LR's 3, and then add it to your 2 products and their ratios compared to the 3 for the LRs. So then we just did a math problem where we subtracted from the reactants, we added to the products, we got these numbers. Now let's go back and see if we can answer all the questions. And you may not calculate them all, but I want to make sure you locate the identifications of everything. So we know the LR is good. How much copper will precipitate? What are you going to do? Have a good word. Right, you would just take this copper, and you can convert to grams by using its molar mass. We're good there. Okay, and then the next question, how much excess reactant is left over? What do you guys do? How much excess is left over? This one, right? This one's the excess one, and you would take that to grams. It's as much as referring to mass. A lot of times the question will say just about one product, so if you read in the question, you're like, hey, I only need to do this one column, that's fine, because they didn't even ask about this other product, so we may not even have to fill out that column, but I want to make sure you're good with everything. Okay, so let's look at, let me get a different one. Favorite plant, stoichiometry. I think so. Okay. So, hang on. Okay, we are going to have to do this one. Yeah, go for it. I want you guys to start. Yes, it does pick up like all the sheet paper. You need to look at your example.
What's the first one?
Versus AG.
And then this yeah. Usually do that, but then
How much silver do you come back? So this is
Yeah.
so that would take 46 years.
You agree with me, don't agree with me on everything. You just immediately trust that what I say is right.
See, I do the same thing with you guys. Like, when you guys tell me something, I'm like, oh, that's right. Oh, no, that's not right. I have to think.
But we have a lot of it.
Yeah.
It's the same way.
We have that first part.
It's all the same thing.
As I said, it's the first, initially, second person.
Stop for 1 second. Has everyone gotten their halves, their before the reaction for your two reactants? 0.09 or 0.0393 copper, and then 0.04 for the silver nitrate. Okay, stop here and somebody tell me if they're confident. How do you figure out who the LR is? Go for it, Lee.
Essentially, like we set it up as
Uh-huh.
times 2 moles of silver nitrate.
Alright, so you're multiplying by 2/1. Now that whole step, this step right here, you can do it on the side of your paper, you can do it in your head, you can do it in your calculator. I want you to be confident though in doing it. Here, straight out to the side, do it. Because what I'm doing in my head right now, I'm not even writing anything down. I'm going, I need 0.0393 times 2. So I need double the silver nitrate than the copper that I have. So I got about, 0.0393 times 2. I need a lot of silver nitrate. Do I have that much? No. Like that's going to be about 0.07 something. 0.07 something, that's how much I need of the silver nitrate. I only have 0.04. So what's going to happen here? It's going to run out first. So what she said was, say I have 0.0393 moles of the copper, and she's multiplying on paper 2 moles of silver nitrate to every 1 mole of copper, and that shows me that I need, like we just said, point oh 0704, 94, something like that. I need a lot of silver nitrate. So that's how much I need of the silver nitrate, but you notice I only have 0.04, so then I'm good to move on. I just don't have enough silver nitrate. So that one's my LR, and that means copper is going to be in excess. So that should be good to move on to the during part. So I'm going to try to let you guys preview the question because I got to move it down.
Well,
Can I go past the question? Is that okay? I know some people are still looking at it. I just going to make this bigger. It's just way too small. Ooh. So when you get to your during part, you should be subtracting 0.04 moles from the silver nitrate. That gives you 0 after. And then the before the reaction, 0.0393 moles of the copper gets subtracted by a ratio of 1/2 because there's 1 copper for every 2 silver nitrates. So that's why I have the ratio of 1/2 here. But I'm adding to the silver made in a 2-to-2 ratio because there was 2 on the silver versus 2 silver nitrates. And I'm adding a ratio of 1 copper copper 2 nitrate or whatever those over here to every 2 silver nitrates. So that's why it's a 1/2 here. So remember, the lower denominator coefficient is talking about the LR. And so that gives us leftover and then excess. So from there, you guys are going to be answering those couple questions. And if you're done with this question, keep working on your crossword. I'm going to put the answers up here there for you. I'm going to try to let everybody keep on getting started. Yeah.
so when you're doing the after first column, you don't take 0.03 and 3, you take 0.074. And subtract. Because otherwise it equals like
This? Not if you do it in a ratio of 1-to-2. Right? Because silver, you have this is how much you have of the silver nitrate, right? You have the 0.04.
okay, so you do that first time. Subtract that.
Yes. Or in your calculator, just do this. Subtract parentheses, this times 1/2 in parentheses. It'll kind of do it for you. Because that should give you 0.0193 moles of copper in excess. I think when you do it, just double check for me. That's 0. And this is the silver. And this is the, oh, that's not, I got the wrong, I got them on a different order on my paper. So those of you who've gotten to the bottom part, did you get 0.093 or 0.0193, 0.04, and then 0.02? Okay, so those will be kind of your foundation of making your answer start. Who got that? Who got that far? Okay, are we seeing any mistakes? Are we seeing where our problems are lying? Probably more than anything, it's just the ratio right here. Just forgetting to put what it is over the LR, what it is over the LR, what it is over the LR. So on the answers for the questions asked, you can figure out how much silver can be recovered, so you'll convert your moles to grams. Reactant in excess, convert your moles to grams. the percent yield if 3.64 grams of silver is recovered from the reaction. So what is this telling you? What yield is that? Actually a good area. That's literally saying how much was made in the lab, actually yield. So on paper, La La Land here on this big table would be our theoretical yield. So looking down at the silver, this was silver. So we would say 0.040 moles of silver. Silver weighs 107.9. Let me double check that. Is that right? Okay. And so then this is going to be your theoretical yield for silver. That is 4.3 grams of silver. Okay, so that's 4.3 grams of silver. Theoretical, it's bigger. This person got what? What's this little thing up for? They got what? 3 point what? 3.64. Okay, so they got 3.64 grams. In theoretical La La Land, they should have gotten 4.3 grams. So I'm dividing, multiplying by 100, and that should be 84%. I would take that person any day. It's pretty good. So, big process, big picture. Are you okay? You're okay. Big picture, you're okay. You don't have to be a perfect human being, specimen of chemistry, but I want you to be okay. So I'm not going to have you do an LR1 tonight. We'll do another LR1 tomorrow in class. What I want you guys to do is either work on your crossword. I'll be taking that crossword up on Friday, and or work on problem set 1 through 3. The problem set, I'm not going to have you guys do the whole problem set. It is a beast. It is worse than problem set 3B. Okay, so if you work well in class, I'm trying to minimize that. So I know you guys have that other thing due Friday, which is what? Experimental design. So I'm trying to leave some time open for that. I will leave 1 through 3 up right here. The true false part, I'm going to scroll past. I'm just going to 1 through 3. So if you want to start that with a friend, there you go. 1 is really easy. Super easy. And now you'll realize that, oh, sorry, before you move on. Now you realize when I gave you this question yesterday, it was like, oh, in the excess of oxygen, when you see the word excess, it is screaming to you who the excess is. So who's going to be the LR? The other one. So there's no need to do the whole LR process. Like in this number 3 here, iron reacts with copper 2 nitrate. How many grams of copper can be collected from iron with excess copper? So I'm telling you copper is the excess, so then iron's the LR, so you just start with the LR amount, which would be the 44.7. There's no LR problem here. There's no question what the LR is. That's why those are easier than we just did today. Okay, so if we're good with 1 through 3 tomorrow, I'll kind of keep it low and do 1 or 2 questions tomorrow. We're good. We're coming. Oh, I never changed it from over here. Albert. You guys have stuff to do. Don't get distracted. Willpower, people. Willpower. No. No, they don't have I don't know. We did the gummy bear.
What is the first tendency? Red?
You can see, if you can get up and see, right? You guys have the time what you need.
Albert, I want to see this.
Ready?
Down, it's just a metallic element. Metallic element.
Metallic element, you it's the blank.
Oh.
It's only 4 spaces.
Yeah, do you have a drop? Oh, wait, it's 5 pounds. Don't know what it is, though. Oh, wait, I know what it is. No, yeah. Real? I thought it was like stuff that we were going to find out. I don't know. And I
think yesterday after the
what about the other farm? Like after
I like chocolate. I like chocolate. It's not like a specific. Yeah, I was like, okay. What element could it be?
It was like what we're doing.
It's overall education.
Well, I'm not learning anything.
You're testing your vocabulary.
I'm definitely learning.
Chemist.
Milligram.
Is that synthesis right? For aluminum oxide?
Synthesis of aluminum oxide, is it with water? Oh, hold on, what am I looking at? Oh, look, from its element. So synthesis of this, that's the product. Oh.
Oh.
And so from its elements, which are aluminum oxide.
Got it.
Okay, that's what
Got it?
I'm
It's similar to what we like we did yesterday.
Yeah, I was thinking that other one was probably from hydrogen.
Oh, that's the same. Wait, what I write? Okay.
Who's the well-known English atom?
It's 23 down. Oh, never mind.
Two is 3 years long. That's what I'm trying to. Maybe after this we'll be okay with meeting. Yeah, it's almost time to go. So I don't have fuel today. If you need to find a location for a friend to sit down and do Mythbusters, then make plans. Because you know that's due Friday. If you want to ask me questions, tomorrow's gonna be a good day to ask questions. So I've got you guys open for TLA tomorrow. If you want to come in and do homework, ask me questions, let's do geometry, Mythbusters, life, whatever. Okay.
Yes, absolutely.
Yeah. Drink enough water.
Probably not.
I don't know the meaning of life. To be honest. I'll work on that. Yes, I'm here after school if you need me. Oh, no. Okay, bye. Keep up, Nicole. You're good, girl. Bye. Bye.
Bye.